Good afternoon, everyone. I hope you guys had an awesome and wonderful weekend. It's Mom J. Today, we're going to be doing a couple of things today. We're going to start out with going over activity 90 and 91 questions. And 91, I'm going to explain a little bit. I know there were some people who are having some trouble with 91, so I'm going to explain a little bit, and then we're going to go over 96. Now, 95 is in the process of uploading. I did record a video, and it is in the process of uploading. So you can watch that at your leisure. We were able to get some pretty good results. So I hope you take a look at that video as well. And that was on selective transmission of light. So it is in the process of uploading. Hopefully it'll be done before this class so that it shows up in order. But activity 95 is coming up. So looking at activity 90, we're just going to go over our questions. And then we're going to go over 91. Activity 90 was a frequency of sound. Okay. And just to give you an idea of what that was, it was a lab where we had the heavy metal washer and the string and the yarn. And I posted the link for it with the lab set for the video. And that was the one I had a really hard time working with, only because I would have needed multiple people. So look at questions. It says waves involve some type of disturbance that cause the energy transfer from one point to another. What was the disturbance that caused the wave in the yarn? Okay, so hi Jake, how you doing? Oh, good to see you. So does anybody want to tell me what the disturbance was, or even before we get started, kind of say hi just to let me know you can see me and hear me? Okay. Oh, wonderful. Okay, so I know Jake can definitely hear me because he's answering me quick. Okay, so the stream's coming through okay? Awesome. Hi, guys. I'm doing okay. Thank you. You know, it was a great weekend, nice and peaceful. So we're almost done, guys. We are almost done. Okay. So hi, everyone. It is so good to see you. All right. So looking at that one, who wants to tell me what was causing the disturbance in that video? Anyone? I know it's typing, so I'll give you a moment to answer. And I'll describe it once again. You had a person in the video that was holding up a washer tied to a piece of string, and then that the other end of the washer was tied to, and they were simply swinging the washer. So what was causing the disturbance? Takers? The person swinging. Yes, the movement of the hand. That is correct. So I don't have it here, but they were holding a string, and that string was attached to a washer. So when they went like this, you see the wave motion was going through the string. All right, so what evidence do you have that the energy was transferred from one end of the yarn to the other? How do you know the energy went from the top of the yarn to the bottom of the yarn? That one is actually fairly simple. You can see the disturbance move down. Correct. If you're swinging it up here, you can see the yarn moving all the way down to the floor. So as it's swinging and you see the disturbance and you see the bottom of the yarn in the video, you can see the bottom of the yarn touching the floor and it was moving. you were able to see that the disturbance carried all the way down. Excuse me 1 second. Sorry, there was a person at my door. Okay, so number 2, that was actually number 1, A and B. Number 2, the frequency of the swing of the washer can be calculated if the time for one swing is known. Suggest reasons why you instructed to measure 10 swings instead of 1 swing. Now, this is a little bit of a review of stuff we've done before. So if you're calculating, if you're only using the time for 1 swing, why did you have to take 10 swings to figure it out? See if your result is consistent to get the average. Okay, if you start swinging at 1, you want to make sure that your swing is consistent. So you want to take the average. So if 10 swings happened in 5 seconds, then each swing was about half a second. Okay, so that is correct. Awesome, thank you. So look at the diagram of the wave below. Describe the motion of the yarn's position at B and C. Okay, so just to give you an idea, I know that you don't have that picture. This is actually the picture. So ignoring from this point on. And you have A, B, C, and D is over here. So A, B, and then C and D. So the question is, describe the motion of the yarn at positions B and C. Okay, so to describe this, the way they're wording it is a little bit confusing, but at point B, your yarn is moving from the highest point back to the minimum point. Okay, so from B to C, it's at its highest point away from the line of origin, and it's moving to its minimum point. And then from B to C, it's moving from the minimum point, it's reaching its maximum point, and then coming back to the minimum point. Okay, good morning. All right, so does that make sense? Does that make sense? Are we good with that? All right, so I'll move on because I'm not really seeing any response, and I'm wondering. Oh, okay, there we go. So there's a little bit of. All right, so between which 2 points is energy transferred? So if you look here, you're from A, B, C, and D. Energy is transferred from point A to point D. Okay, and the reason it's transferred from point A to point D is because you're starting and ending at those 2 points. Okay, all right. B. Oh, I'm sorry. Yeah, 4. All right, so we did A and B there. Number 4. Look at the diagram from the previous question above. Draw what the wave would look like if the frequency were doubled. Okay, and it's kind of drawn. I'm looking at my diagram through the camera. It's kind of drawn, but you know, it's not perfect. But basically, if the frequency doubled, it would be 1, 2. That's all it would be. Okay. And B, what would the wave look like if the wavelength were doubled? Okay, so this one is a little bit different. Okay, so if instead of doubling the frequency, you double the wavelength, and I'm going to take this off. So here, you know that a wavelength is from one point of a wave and it would be to the exact same point on the next wave. But if you were to double the wavelength, it would now go as such. In other words, if you're doubling the wavelength, the size of the wave would increase. So, number 5, match the following description of people to their audiogram. Okay, you guys got, and I'll just show you the picture so that you know what it is that I'm looking at. But you had these audiograms, and what you had to do was match each of these descriptions up here to these audiograms here. Okay, so I'll just go ahead and explain it. So in the first one, for Jose, you had decreased hearing in the right ear at higher frequencies. So if you look at all 4 of them, red is left and blue is right. So you'll notice here at higher frequencies, the right ear is down, but the left ear is normal. So that would be the correct audiogram for Jose. Leon, who is 68, has not noticed his hearing change because it has happened so gradually as he aged. However, he has more trouble deciphering women's words. Now, I'll explain what that means in a second, but let's take a look. We're looking for something that diminishes gradually, so over time. So if you were to look at these 2 over time, okay, audiogram 2, because this one increases again, okay, audiogram 2 shows a diminishment over time, and the higher frequencies is where there's the biggest problem. Now, why is that important? Well, women tend to have higher pitched voices than men overall. So if women tend to have higher pitched voices than men, the wavelengths of their voices are going to be a little bit faster. They're going to be at a higher frequency. Okay. So if he's having trouble hearing women's voices, that means he's having trouble hearing higher frequencies. The audiogram that most closely matches that is audiogram number 2, where the higher frequencies have diminished over time. Okay. For number 3, or C, Shannon has mild hearing loss involving sounds of 3 to 6,000 hertz. Well, if you look at here, okay, 3 to 6,000 hertz. Well, I'm trying to hold it so you can see it. Here, this is at around a little past 2,000. At 3,000, you have a huge dip, and you see an increase again somewhere between 6,000 and 8,000. So that is the range here, and therefore that would be the I'm sorry, right here. That would be the diminished loss within that particular range, and as a result, that will be Shannon's audiogram. And Sophie has less than 50% hearing in both ears. Well, the only audiogram that shows 50% hearing in both ears or less loss is this one down here. You see everyone else starts up at the top, but she is at less than 50%, so she's down here. Okay, does that make sense? Okay, hopefully that made sense to you. Okay, now 91. No. Wi-Fi, I'm gonna have to look up a good explanation for you, but Wi-Fi actually is what allows the transmission, because Wi-Fi waves, I guess you could say they are a type of sound wave. But they allow you're transmitting connectivity there. I'm gonna have to look up an exact definition for you. I don't have anything to do it here right now, but I'll look that up and I will let you know tomorrow. Please don't let me forget. Send me an EDSB message and I will look that up so that I can get an exact explanation, because it's escaping me right now. Okay, 91, longitudinal transverse waves. All right, there were some people that had problems with the difference between a longitudinal and a transverse wave. So I'm going to show you what they are again. I apologize. I know this is a tendency of making noise. But longitudinal, if you look at, okay, so you're transmitting energy along the length of the slinky. Okay, so as an impulse is passing through, and you can see it when I do it really fast. Okay, you can see the compression and the rarefaction between them. Okay. So if you look at the length of the slinky, you can see the compression and the rarefaction. Okay. And a longitudinal wave, okay, if you were, transverse, okay, and it's moving kind of quick, but basically it's the wave that goes like this. So as you have one person that's holding it and the other person that's there, and the longer you get, then you can actually see all the wavelengths, although I can't really fit it within the screen. Okay, but you can see the energy transfer, you know, across the slinky. So that is a transverse wave. So with a longitudinal or rarefaction wave, you have movement that's going across the slinky this way. For a transverse wave, you can see the movement away from the origin line going that way. So hopefully that helped a little bit. I know some people were having trouble, but that's basically the difference. It's the motion of wave, and it's the way energy is transferred throughout the wave. Okay. Looking at the questions, and I know some people had a lot of problem with the questions, so I really do want to explain those to the best of my ability. Number one, it was create a larger version of a Venn diagram shown below. Record the characteristics of longitudinal and transverse waves in the circle with the label. So you're looking for 5 to 10 similarities and differences. Okay, so the difference between the similarities between a longitudinal and a transverse wave. So what makes them similar? Okay, so both waves, in the example of the slinky, both waves had energy that was being carried across the metal spring. Okay, both of them do carry energy. They both have frequency and wavelength. Okay, longitudinal waves, movement is parallel to the propagation of sound. In other words, if sound is coming here, the movement is parallel. So it's going in the same direction as the sound. So you have the disturbance coming here, and the movement is going across the slinky. For a transverse wave, movement is perpendicular. So the disturbance is here and movement is either actually going up or down. Okay, so movement is up or down to a disturbance that's coming in this direction. Okay. Now, describe what happens when a longitudinal wave pulses hit the floor in part A. So in part A, now just to give you an idea what part A and part B was. Part A, and I know I didn't explain this when I did the video, so I apologize. Part A, you were doing a longitudinal wave, okay? And in this particular case, the longitudinal wave was this way, and it went to the floor. Okay, so as I created a disturbance here, now you can't see the floor, which is one of the reasons why I didn't do it that way. But as I create the disturbance here, the movement, the compression and rarefaction that you're seeing in the wave, okay, moves towards the floor. So for that particular question, okay, for part A, the longitudinal wave pulses hit the floor. In part A, the pulses bounce back upward for a short distance. So I'm sure you saw that happening here. I know it's a little bit difficult to see, and I'll stand in front of it, so hopefully you'll have a better field of view. But some of you may see this type of motion. Okay, so as a pulse, yes. So I'm going to take this temporarily here so that it's not the slinky that's bouncing. But as you look at, okay, as I release, how many of you notice you can see it goes down, but then bounces up slightly for a short time? So the wave is moving, the disturbance is going this way, the wave is moving in the direction of the disturbance, goes down and bounces back up for a short time. Okay, does that make sense? Now for a transverse wave, a little bit different. Transverse waves pulse reach the holder in part 2. Okay, and the pulses bounce back towards the person who is making them. So as we're like this, okay, it's reaching, this person has to hold it still. It's hard to do both. Okay, but it's reaching over here, which is why this hand is moving. I'm not moving it. It's being moved by the motion. But I also feel a disturbance back in this hand. Okay. For 3, what happens in part B when the spring is stretched double to its length? Well, it's hard for me to do that. I can do that with a portion of it. Okay, so if I go like this, for example, but if I go like this, so same speed, but when I stretch it double, it moves faster. Okay, so the wave travels faster, the amplitude is decreased. So it doesn't go as high when I stretch it out, but the wave is moving faster. What happens to the, okay, 4 and 5 were the ones with the biggest questions. What happened to the amplitude of the wave pulse when it traveled along your spring in part B? Suggest an explanation. So when it travels along the spring in part B, the wave pulse gets smaller and the amplitude decreases. Okay, so as the wave is traveling across in part B, just so you know, okay, I'm gonna go ahead and tape this again because I can do this way. Okay, so part B. I'm afraid it's gonna pull off. Okay. Now I've got it. Oh, yeah, it does pull off because I'm putting a lot more pressure on it. So I'm gonna try to show it to you in such a way and unfortunately you can't see the whole thing, but as it travels along the spring and gets closer to the floor, the amplitude decreases. Okay, so where it's wider up at the top, it's smaller at the bottom. Okay, and that's because over time it does lose energy. Energy is transferred to sound, okay, frictional forces, so on and so forth. And number 5. Make 2 tables like the ones on the next 2 pages. Okay, so a lot of people are asking me about this. I don't know if you saw it, but I actually posted this table and this table on Edsby. Okay, so the question was, make 2 tables like the ones on the next 2 pages and fill in the missing diagrams to show a change in amplitude or frequency. So what they wanted you to do is they wanted you to diagram an increase in amplitude, decrease in amplitude. Okay, so what happens when you move the waves away from each other? You move the slinky closer, further, so on and so forth. So, and the second one, frequency. So frequency, obviously, it's to do with increasing the wave. Okay, and this is going to be hard to see, but basically what you can see here in this particular case, you can see the differences between here. This is a little bit wider. This is narrower. Okay, so this decreases. This is your starting point. This decreases. You can see that the springs here are much further apart. Okay, here, this is your starting point. If you decrease the amplitude here, obviously they don't go up as high. Okay, here, if you increase the amplitude, this is what it looks like. All right, for frequency, if you decrease the frequency, you can see here the compressions. You have less compressions here. If you increase the frequency, you have more compressions here. Here, increasing you start out with this frequency. If you decrease the frequency, you have less wavelengths. If you increase it, you have more wavelengths. So hopefully that helped you understand what they were trying to get you to understand there. Okay, does that help with that? Do you understand what they were looking for now? Because I know that there were a lot of people who struggled with that. So I wanted to go over that and make sure you understood it. Okay. Now, if you have any questions, please feel free to let me know. I'm going to go ahead and move on with 96, which is what we should be covering today. 97 and 98, I believe, are another recording. And 99 is our last activity. And then, guys, we're done. So I will create a recording for 97 and 98. They go together. They're relatively short. They do go together. 95, as you know, I mentioned earlier in this session that it is a recording that is in the process of being uploaded. Hopefully it will be done soon. And I'll post the questions for 95 a little bit later. I didn't want to hit you guys with too many questions at one time. I didn't want you to have to feel that you had to get all of those questions done at the same time, which is why I held off on posting. Okay, so we're going to be looking at the electromagnetic spectrum today. So sunlight is a combination of light waves and various frequencies. Some of the frequencies can be seen and some cannot be seen by the human eye. The reading in this activity explores the nature of waves, which are electromagnetic. An electromagnetic wave transmits energy across distance as moving electrical and magnetic fields. So Herschel's famous experiment. In 1800, British astronomer Sir Frederick William Herschel made an important discovery. While observing the sun through colored lenses, he noticed that some of the colors of light felt warmer than others. This observation interested him so much that he designed an experiment to try and measure the temperatures of the different colors of light. In his experiment, Herschel then used a prism to separate light into the colors of the rainbow. He then placed a thermometer so that it only was struck by one color of light at a time. He discovered that red light caused a greater temperature increase than green or violet light, as shown in the diagram at the left. So there's a diagram, okay? And you can see that he has thermometers that are hitting different, that are being exposed to different colors. And red caused the greatest color increase, the greatest temperature increase. To his surprise, he also noticed that the temperature increased even more when the thermometer was in the unlit area just past the red end of the spectrum. The only explanation for this data that made sense to Herschel was that sunlight must contain invisible calorific rays. Herschel performed other experiments and found that these waves behaved just like visible light. They were reflected, absorbed, or transmitted. Because these calorific waves, like calories, because these calorific waves have a frequency just below red visible light, later scientists in 1881 established a name for them, infrared. This name was chosen because the prefix infra means below. Okay. Herschel was the first to detect an electromagnetic wave that was not visible to humans. And the reason infrared heats things up more than visible light is because, sorry, I'm trying to turn my watch off because for some reason it's picking up a lot of messages. The reason infrared heats things up more than visible light is related to its frequency. When infrared hits the molecules that make up many substances, it is often just the right frequency to be absorbed by the molecules. This increases the molecule's energy. The increased energy makes the molecules move faster, which heats up the substance. In a separate process, warm objects also give off infrared radiation, as well as other wavelengths of electromagnetic energy. A year after Herschel's experiment, Johann Wilhelm Ritter in Germany decided to find out if there were waves beyond the violet end of the visible spectrum as well. He conducted an experiment similar to Herschel's, but directed the light onto a chemically coated paper that turned black when exposed to light. He chose this chemical, silver chloride, because it darkened more at the violet end of the spectrum. When he separated the light, the silver chloride was darkest just beyond the visible violet end of the spectrum. He called them chemical rays, which later became known as ultraviolet, because ultra means beyond. So infra means below and ultra means beyond. Okay, and if you look at the electromagnetic spectrum, you have radio waves, microwaves, and then infrared, which is right before red in the visible light spectrum and just below red in the visible light spectrum. So it moves slower than the red. And then you have Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And then you have ultraviolet light, which is just past the visible light spectrum on the violet side. So it's faster than that. And then you have radio waves, microwaves, infrared radiation, visible light, ultraviolet. Then you have X-rays and gamma radiation. Okay. So ultraviolet waves transmit more energy than infrared and visible light. In fact, ultraviolet has the most energy of all the waves that commonly reach the Earth's surface. The energy transmitted to us by ultraviolet waves can be helpful. For example, human bodies transform some of the sun's ultraviolet energy into vitamin D, which is necessary for bone growth. Those people whose diets lack vitamin D and do not have much sun exposure may develop a vitamin deficiency. This results in a bone growth in children in defective bone growth in children or soft bones in adults. Lack of sun exposure, including ultraviolet wavelengths, also results in seasonal affective disorder for some individuals who are prone to depression. Scientists have invented machines to which which use ultraviolet light to sterilize equipment because it destroys bacteria, viruses, and mold. You may have heard of this recently. They were thinking about using ultraviolet light to destroy coronavirus. There are some machines that are used to sterilize. In fact, our goggle cabinet in our classroom, when I turn it on, which I don't do when anyone is in the classroom, it's actually under lock and key where you put the goggles in, you close it, and then I have a knob that turns and it works for an hour. That's actually an ultraviolet light sterilizer. So we have an ultraviolet light sterilizer in our classroom. So at the same time, high energy of ultraviolet waves poses a danger to people and other living things. They cause damage to living cells, which can result in cancer and cataracts, like those in Tia Anna's eyes in the previous story that we did. Ultraviolet waves also cause materials such as those in clothes, furniture, curtains, and car interiors to fade and become brittle. So light from the sun, Herschel and Ritter's experiments showed that there is more energy in sunlight that meets the eye. As shown in the diagram below, most of the energy that reaches the Earth is in the form of infrared, visible, and ultraviolet light waves. The diagram shows that much of the energy given off by the sun never reaches the Earth's surface. This happens because gases in the Earth's atmosphere reflect and absorb some of the energy. The atmosphere acts as a shield that protects all living things from most of the very dangerous high-frequency, high-energy ultraviolet waves, X-rays, and gamma rays. Although ultraviolet light has less energy than other high-frequency waves like gamma and X-rays, it poses more of a hazard to living things because of the large amount of it that the sun emits. If Earth's atmosphere did not have a thick ozone layer, much more electromagnetic energy would reach the Earth's surface, causing harm to living things. So I'm sure you've heard in the past talk about how the ozone layer helps protect us. The ozone layer helps protect us because it shields out harmful UV rays in addition to the X-ray and gamma radiation that is emitted by the sun. In areas where the ozone wave is thinner, because it's thinner, it's letting in more of those harmful rays, and you do have evidence of organisms that are dying or that are being born with severe mutations. So the electromagnetic spectrum, in addition to infrared, visible, and ultraviolet waves, the sun emits a large amount of other kinds of invisible electromagnetic waves. They include radio waves, microwaves, X-rays, and gamma rays. Together, the continuous range of all possible electromagnetic frequencies make up the electromagnetic spectrum shown below. And this is the electromagnetic spectrum here, and I will post a picture of this, but radio waves are here. You see they have a longer wavelength, a much slower frequency. And gamma radiation is all the way at the other end. It has the fastest frequency. It has the shortest wavelength. Okay. Although portions of the frequencies of the electromagnetic spectrum are given specific names, such as radio, visible, and X-rays, the categories overlap. This is because wavelength ranges in which scientists classify each type of energy are somewhat arbitrary. It is often hard to distinguish where one group of wave ends and the next one begins. Fundamentally, all electromagnetic energy is of the same nature. For example, all electromagnetic waves travel through the medium or through a vacuum. They can be reflected, absorbed, and transmitted through various materials. The degree to which each type will reflect or absorb or transmit depends on the wavelength of the wave and the surface it hits. Now, visible light travels through space very quickly, still travels through light and through air and water very quickly. At an opaque substance, like this book, for example, if I were to shine a small pinpoint light here, it would not travel to the other side of the book. You can shine it through a translucent or transparent window, but you can't shine it through an opaque object. Now, there are certain waves, X-rays, for example, that will travel through certain types of solids. When I used to work in a hospital in the ER, one of the things we had to do was have our walls were lined in lead. And the reason for that is because lead could stop an X-ray. And if we had to have patients use a portable X-ray machine, you could not be on the other side of the wall where that X-ray was pointed. So for example, if a person is sitting here and the X-ray is coming from this direction and being shot at a person this way, the wall that was behind them, no one could be on the other side of that wall because they could potentially be exposed to harmful X-rays. So to help mitigate some of that, electromagnetic waves such as X-rays, when those are being utilized, the surrounding areas are lined in lead so that the X-rays don't penetrate those walls. Okay. So, although electromagnetic waves have common properties, there's an astounding difference in wavelength from one end of the spectrum to the other, which I showed you. The range of each wavelength from gamma rays to typical radio waves is over 1,000 meters. Each range has some unique characteristics. Short wavelengths from those from ultraviolet and gamma rays have an ability to penetrate living cells and damage them. Longer wavelengths of energy, like those in the radio range, can be generated or received by antenna. Our eyes can only detect a small range of wavelengths from 380 to 750 nanometers. Okay, and just so you know, 1 nanometer is 1/1 billionth of a meter. So we are only able to see in this wavelength, in this area right here. Everything else is outside of our field of spectrum. So there are hundreds of applications of electromagnetic energy. For example, X-rays are used to scan bones and teeth. Remote controls send infrared signals to devices, and Wi-Fi relies on radio or microwaves to send and receive data. So there's the answer to your question. Wi-Fi relies on radio waves or microwaves to send and receive data. Microwave ovens create microwaves to transmit energy to water in food, thereby heating it up. So Wi-Fi is not a type of wave, it utilizes a type of wave. Some technologies allow us to extend our senses by using electromagnetic waves. One example is infrared imaging in night vision goggles. Night vision technology lets us see objects by changing the invisible infrared light given off by objects into an image we can see with visible light. Since warm bodies give off infrared energy, a person wearing night vision goggles can scan an area to see people and other warm-bodied animals in the darkness. Additionally, there are detectors that can sense all kinds of electromagnetic energy. For example, astronomers use radio telescopes that detect radio waves by which astronomers see distant objects in the universe. So I can post that reading if you like. I will also post the analysis questions. And just to let you know, 97 and 98, as I mentioned, are recording, but tomorrow I will go over 93 and 94. Okay. Wednesday, I'm not, oh, actually, I'm sorry. No. I apologize. I'm going to go over 93 and 94 on Wednesday. There is no class tomorrow. Tomorrow, teachers are being brought in, or specifically the science department is being brought in to do our classroom procedures. So I have to clean out the classroom and get it ready for the summer. So we are not having class tomorrow. I will resume class Wednesday to go over 93 and 94. And Thursday, I will go over 95 and 96. And next week, we will only have class on Monday and Tuesday, maybe Wednesday, I'm not sure yet. I will go over on Monday, 97, 98. I'll go over those questions, and we'll talk about 99, and probably wait until Wednesday, skip Tuesday, wait until Wednesday, give you some time to work on 99, and we'll go over 99 and we'll be done. So I'll also mention that in EDSB as well. So class is pretty much done. I hope that was helpful, especially those of you who have questions on 91. But if you have any questions, please feel free to send me a message and I will be happy to answer you. And I hope you guys have a wonderful day. I'll see you tomorrow, or I'll see you Wednesday. Bye.